Okay, so last time we did this integration. We were talking about moments of inertia. Moments of inertia is the effectiveness of mass at causing inertia, causing a reluctance to accelerate in rotational terms. And it turns out it significantly depends upon where you are, not just how much mass you have. How much mass you have does matter, but it really depends upon where you are. So it's an R squared relationship, R being the distance from the turning axis that we're interested in to where the mass we're interested in is. And we can do things like this where we look at discrete masses at certain points from a turning axis. So we saw that this guy was a certain distance away and this guy is a certain distance away. So this is a certain distance away. And if I changed my point of interest, so if I changed and said, oh, I want to put my point of interest there, I would have different distances. And so I would completely change my moment of inertia about this new point. So you can think of an object as having an infinite number of moments of inertia. And then we say, well, what about, can we integrate, can we make something up into such a small array, such a big array of tiny little masses that I can do anything? And in principle you can. And if I had a complicated shape like a teacup, then what would I do? I'd basically go to my computer, I'd do an infinite number of, a large number of points. I'd break this up into little cells. And there's a whole science about how you do that, by the way. A lot of weather forecasters have to do this. And how you pick your cells so that you can sample in an appropriate way. So that you don't overwhelm the computer, you get the most efficiency out, but you don't have sampling artifacts in there. There's a whole science in that. But, if I have a big enough computer and a small enough object, I can divide this up into a whole bunch of points. I can take my point of interest and I can say, all right, what's the moment of inertia for all those points about that? And it'll work. Alternatively, I do the physicsy trick, which is I go with high degree of symmetry to make the math easier. And then what I do is the classic one that we look at is the solid cylinder, and we're looking through the central axis. We're looking through what we call the central symmetrical axis. We're not looking along the side. We're not looking for an axis through there or through there. We're looking through that central circular axis of symmetry. And we can work that out, and that's what we did. There's other things we could do. We could do the hollow hoop, and we don't do the hollow hoop. It's just a longer integration. It's a bit more picky. And so my sense is I'd sooner do this solid one with you, but tell you that's coming up, so learn how to do it. And then my sense is once you learn to do that, if need be later on, you could have a look at some of the others and the solid sphere as well. It's like, and then we sort of said, well, hold on. If we did these integrations, what would we find? And you are responsible for knowing these. And I do apologize for this. I got all clever and got everything over the base 10, but that's not how you see it in the books. It's 1 mr squared. It's 1/2 mr squared, and it's 2/5 mr squared. And if you see it in your notes and you see it in the book, then it reinforces itself. So rather than 2/5, so rather than being clever, it's better off to do it like that. And let's look, solid cylinder. Let's make this, let's do a hollow hoop just for the fun of it. So a hollow hoop has a radius of 4 meters, a mass of 2 kilograms. What is the inertia about? Its circular axis. So here we have the thing. Now, this is a narrow pipe. It's not like a washer where you have a big flat plate and you have a little hole. That won't work so well. We're really thinking about having something where it's mainly open space in the middle and all the metal or the ceramic is round the edge. Because we simplify that in our math to get this. And if we can live with that simplification, then what we find is that our I hollow hoop is equal to, and for our hollow hoop, it's just the mr squared. So it would be the total mass, which is 2 times radius is 4 squared, which is going to be 16, 32. 32, and that would be kilograms meters squared. So we see that, you know, it works out a number. So you know, it's 1 mr squared, 1/2 mr squared, 2/5 mr squared is the way. I remember being on one of those rides at Busch Gardens where you're going down a river and there's like maybe 8 or 12 people sat in a raft. And, you know, it starts to spin just because of eddy currents in the water and all that kind of stuff. And you start to spin. And I remember people spray you with water from the bridges and all that kind of stuff. So it's on a hot day, it's kind of really nice. And near the end, you kind of come off this one little bit where you're kind of swooshed over this like side, and it kind of sends you towards a wall. And I was quite struck by how the turning effect changed when we hit that wall. It was like everything slowed down. Because our motion went from turning around there, in the water we turn around our centre of mass. So we just rotate around that bit as we're floating down the river. But when we touch the wall, we rotate about that bit. And so suddenly our rotation axis is shifted over to one side. And if you imagine, now we're trying to rotate everything round here. And so suddenly we have a lot of mass that's a long way away from the turning axis. So it tends to make our moment of inertia suddenly very big, which tends to slow down all the rotation. And so the question is, can I work out what that moment of inertia is? And there's a thing called the parallel axis theorem. It's called the parallel axis theorem because if you look at this thing from the side, there's one axis of rotation there, and the parallel to it is another axis of rotation. So those two axes have to be parallel. You can't have that. You can't say, oh, you know, I know my moment of inertia around that axis, now I want to know it about that axis, and use the parallel axis theorem. It won't work. The two axes have to be parallel. If they are, then we can say that our moment of inertia about our point of interest is equal to our moment of inertia about our centre of mass plus another term. And what I'd appeal to you is, I mean, learn the equation, but you don't, it's not that hard to learn it if you use your physics underpinning. We learned in chapter 1 that things on both sides of an equation have to have the same, effectively, the same dimensions, which is basically the same units. And if my units for my moment of inertia are kilogram meters squared, and I'm adding another term to take into account this shifting of the axis, it's still got to have units of kilogram meters squared. It can't have anything else. So I know it's going to be md squared as opposed to m squared d as opposed to d squared or m. There's things it can't be. It can't be some wacky combination of m and d. It's got to have the same units because we're adding it. And when you add things, you can't add tanks to bananas. It makes no sense. You add apples to apples and oranges to oranges. You've got to add the same thing. So if it's kilogram meters squared, then when you add a term, that's got to have units of kilogram meters squared. You can't say whether it's got a prefix in front, a coefficient in front of it. Maybe there's a half, maybe there's a quarter. I understand that. But it's not going to be md cubed, you know. So in your memorization, I'd love you to know this equation, but if you're kind of most of the way there, don't make a mistake by putting down md cubed, because that physically cannot be true. So your physics tells you, oh, it's got to be something like md squared. Maybe there's a number in front of it. I don't know. If you're going to make a mistake, put a number in front that shouldn't be there. But don't put the wrong units down, because that's fundamental. That's something that can guide you in all your equations. When you look at an equation, you write it down. Most of the time I'm seeing that, and I think it's because the exams are a bit delayed from when we actually do the work. I thought it would actually help, but it's certainly not helping with people remembering equations. And often they're putting down equations that physically cannot be true. Because if you have acceleration on one side, you've got to have acceleration on the other side. However you get there, you've got to get it. And you can't have velocity equals acceleration. It can't work. And when I see people writing down the equations, that's what they're giving me sometimes. So this is coefficient of 1, if you like. So it's basically that. So a body of 4 kilograms has a moment of inertia about its center of mass. So let's just a potato or whatever. There's its center of mass. I center of mass. I center of mass is equal to 6 kilogram meters squared. This mass is equal to 4 kilograms. What is the moment of inertia about another point on the body that is located 2 meters from the center of mass? So I'm going to go here 2 meters. So that distance there, that's 2 meters. And this is I of interest. And what I know is that I of interest is equal to I center of mass plus, it's going to be md squared. So I of interest is equal to 6 plus, it's going to be 4 times 2 squared. I is equal to 6 plus 2 2s are 4, 4 4s are 16, which equals 22 kilograms meters squared. It doesn't get smaller. I mean, it's always a plus sign, so it doesn't get smaller, and it quickly gets bigger. As soon as you go further away, it gets bigger. So when we hit the side wall with our rotating little raft, it suddenly slowed down. The rotation suddenly slowed down. Which kind of leads us on to just a couple more things. So let's look at the energy inside a system. So I have linear or translational, or whatever you want to call it, kinetic energy. The kinetic energy we did in the past was half mv squared. It takes energy to rotate. If you ever went to they've got one outside the Glazier Children's Museum. If you get one of these things that go round and round and round that kids sit on, and you start trying to spin it for them, it takes a lot of energy to get that thing going. So it takes energy to rotate, and the energy of rotation equals a half I omega squared. A system consists of a body having a moment of inertia of 5 kilogram meters squared, which rotates at 3 radians per second about a turning axis. What is the rotational kinetic energy of the system? So Ke rot is equal to 1/2 I omega squared, which equals, what do I know? I didn't do my visualization here, which is bad. So I have my I is equal to 5 kilogram meters squared. And I should really say, see, this is bad language. I should really say a system consists of a body having a moment of inertia of 5 kilogram meters squared about axis O. Because, you know, it could be about some other axis. So I should have tightened up on that. Which rotates at 3 radians per second. So omega is equal to 3 radians per second, about this turning axis. what's the rotational kinetic energy? So I'm given that, that's 5, and I'm actually given that, this is a piece of cake. So that's going to be 3 squared, which is 5 nines, that's 45, and it's going to be joules. So in principle not so bad, it's just you got to know those numbers. I could dress it up a bit, yes. Oh, forgot my 1/2. Yeah, sorry. It's going to be one of those days, I think. Over 2, which equals 22.5. Thank you. I could have dressed it up a bit. I don't have to give you the eye. I could give you the mass. I could give you the radius. I could give you the shape. And you've got to work out what the eye is, you know. I suppose I could give you the tangential velocity and have you use that Vt equals omega r. So I could somehow incorporate that, and I could somehow incorporate that that is equal to 1/2. Let's say this is a solid cylinder. That's a 1/2 mr squared. So I'd have you remember that, I'd have you remember that, and then I'd have you remember that. So it's a triple decker. But they're all equations that we've messed with, you know. So I could make it a bit more interesting, a bit more straightforward. Let's put it together. I want to talk about things rolling. And the first one I'm going to do is rolling along the horizontal, and the second one I'm going to do is rolling down a hill. That's really what I want to go to. I can analyze this motion in 2 completely different ways. I can think of it as being, so I've got an object, a can, a disc, a solid cylinder rolling across the floor. I can say, well, its center of mass has a translational velocity. It translates the thing from one place to another. And superimposed on that, there's a rotation. So if you imagine getting a camera, you're looking forever at that center of mass. And you're watching the center of mass move sideways because the camera's moving sideways, and you're seeing the thing spin. So I'd say, well, it's a 1/2 mv squared because that's the translational kinetic energy, plus 1/2 I omega squared. So this is my trans bit, and this is my rotational bit. And I add them together. So when it says Ke total, there's a good hint. I'm looking for, you know, these 2 bits of the rotational motion. But if I was to bring my camera down and look at this interface, then I could interpret this whole thing in terms of a rotational motion about this interface. And the interface just moves along. And for this would be a 1/2 I omega squared, but the I's are not the same. In this case, the I's are different, they're not the same, and neither are the omegas. The omegas are not the same. They're different because, you know, they're different. I prefer the left-hand side. It just comes more naturally to me, I think. The right-hand side I don't feel so comfortable with, but it's, you know, it's there. A cylinder of 4 kilograms, 3 meters radius rolls along a surface with a translational kinetic velocity, translational velocity. V-tran is equal to 6 meters per second. And what's its total Ke? So Ke total is equal to Ke trans plus Ke rot. So I better put my rot stuff in. There's my omega, and here's my, so then I say, okay, well, Ke total is equal to 1/2 m v squared plus 1 half I omega squared. So KE total is equal to 1 half mv squared. Now let's think about this. This is 1 half. Now this is a cylinder. I shouldn't say solid cylinder. I should have said solid cylinder. This is old writing and then the new understanding. So I would say solid cylinder. I could say hollow hoop. Could say solid sphere. But I'd tell you what it is. And for the solid cylinder, this is 1 half m r squared. And then my omega, well, remember that Vt is equal to omega r. So that means my omega is equal to Vt over r. Now, I've got to be a little bit careful here. This is V tangential over r. And so the question arises, how are these two related? How does my translational velocity compare with my tangential velocity, the velocity of the outside bit of my disk? Because that's what that is. That omega squared is equal to V tangential over r.
Wouldn't it be the same?
I'm sorry?
Wouldn't it be the same because it's on the tangent every time?
So it is exactly the same. You're perfectly right. And it took me a while to convince myself that that was true. And this is what I did. This is how I convinced myself it's true. And I got some kitchen towel and I basically put it on a counter and I put my finger there. And I put my finger in the little hole thing and I just moved sideways. And what I saw was I ended up with, you know, one roll, one towel, two towel, one sheet, two sheet, three sheets as I moved this thing sideways. I said, oh, I've moved 3 sheets sideways. So this would say my V tran is equal to 3 sheets per second set, you know. And then what I did was I put the kitchen towel over here and I grabbed hold of the towel. Again, I put my finger in the middle and I pulled it that way. So I end up with 1, 2, 3. It's the same effect, and yet this is the tangent moving. So this is V tangential is equal to 3 sheets per second. So for me, when I saw the towel move, when I saw the roll move, somehow that convinced me that that translational was 3 sheets per second. And when I just basically pulled this the other way, so I ended up with the same outcome, I saw the thing spin. Then I said, oh yeah, the tangential is 3 sheets per second. And for me, that did it. And I'd read it in the book, and it didn't convince me, but for me, that did it. So whether you do it one way or the other, be assured that your V translation is the same as your V tangential. So that means that I can use the same V for it. And I can say, oh, it's V squared over R. V over R all squared. So KE total is equal to 1 half mv squared. And let's have a look. Your R's are going to go away, aren't they? They're going to just disappear. So your R's, and I should have used the same R. Man. Sometimes they're not the same R, but sometimes they are the same R. I'm sorry. I'm going to just slow down a little bit. Let's just write this out a little bit more. Plus 1 half times 1 half m r squared times, and this is going to be v squared over r squared. Remember, you've got to multiply, you've got to square both top and bottom. Now I can cancel. And I'm going to go, well, that r squared is the same as that r squared. And I get that KE total is equal to 1/2 m v squared, plus half times a half is a quarter, 1/4 m v squared. Ke total is equal to 3/4 m v squared, which equals 3/4. My m is 4. My v is 6 squared. So Ke total is equal to 6 sixes are 36, and 3 times 36 is 108. And it's going to be joules. Oh, I'm sorry, I need to get this. So 108 joules. And this is the game you play. If I had a hollow hoop, that would have been 1. So it would change the size of this fraction. If it was a solid sphere, that would be 2/5. And it would say change the size of this. But the rest of it's all the same. The rest of it's all the same. Notice that R was completely irrelevant. And so sometimes I'll give you the R just because see what you do with it. And sometimes I'll leave the R out, and it's kind of like catches different people. For some people, they worry about the fact that I didn't use the R. And then for other people, they'll worry about the fact that the R's not given when you don't need it. And if you just write down your principle, if you write down this and you substitute in and you substitute in and you substitute in and you substitute in, and you say the basic physics is okay, I'm letting the math take care of itself, it'll all fall out. But if you're trying to figure out in your head, well, what would the translational be, and then what would the kinetic be, then you'll get anxious about things. Let's make it a little bit more interesting. So now we have a system where I'm going to take an object, a disk, a solid cylinder, a hollow hoop, or a sphere. I'm going to lift it, and in lifting it, I put energy into it. I put gravitational potential energy into it. And then I'm going to let it go from the top of a ramp. And I'm going to see, well, how fast is it going to the bottom of the ramp? I'm using the principle that it's an isolated system. Isolated system means no friction. But I do have friction, otherwise the wheels won't turn. But it's static friction. This brings us back to this kind of, it's a little bit uncomfortable, this idea that kinetic friction is when your tires slide across the road surface and you leave in those black scraping marks on the road. That's kinetic friction. Static friction is when your tires are rolling and you're not transferring energy to heat, particularly when your tires are rolling. There's a little bit of heat because of the rumbling of the tires and, hitting bumps and all that kind of stuff. But you're not scraping the tire across the road. That creates a lot of heat, etc. It melts the tire. I mean, that's how your tire ends up on the road. In this case, I'm going to have a rolling motion. So I need some friction, but it's static friction I need. So there's no transfer of energy from the mechanical system to the thermal system. So I can say the energy at the top equals the energy at the bottom because it's an isolated system. So we say 4 kilogram hoop, hollow hoop, that is 2 meters radius, is placed at the top of a 30-meter tall ramp. It rolls to the bottom of the ramp without slipping. What is its speed at the bottom of the ramp? So I'm not giving you the slope angle because you don't need it. I'm saying that m is equal to 4 kilograms. I'm saying that r is equal to 2 meters. I'm saying that h is equal to 30 meters. And what I can say, this is a hollow hoop. And what I can say is that my mechanical energy at the top is equal to my mechanical energy at the bottom. At the top, I've only got potential energy because it's not rolling, so there's no kinetic, there's no rotational kinetic, there's no springs anywhere. So I can say at the top, I have mgh is equal to, at the bottom, there's no mgh, there's a half mv squared plus 1/2 I omega squared. Do you see where those two terms come from? One's my translational kinetic and one's my rotational kinetic. Why no mgh? Because you're at the bottom. And why no half kx squared? Because there's no springs. So then I say, well, okay, mgh is equal to 1/2 mv squared, which equals 1/2. Now this is a hollow hoop. So this will be mr squared. And then this is omega squared, which is v over r squared. That should be plus. So mgh is equal to 1/2 mv squared plus, this is going to be 1/2, oops-a daisy, 1/2 mv squared. The r's cancel. I'm sorry, I keep missing this step out, and I'm a bit worried that people will just not follow it, so I'm going to just do one more step. And then I'll do that. So I'm going to say, okay, I'm going to go, it's a half mr squared times v squared over r squared. So mgh is equal to 1/2 mv squared plus, and this is going to be 1/2 mv squared. And we cancelled before, we sorted out before that the tangential velocity is the same as a translational velocity, so we don't need to dwell on that. If you want, put down v tang equals v tran to remind yourself of that. So mgh is equal to mv squared. That's interesting. So that means that v squared is equal to mgh over m, which equals gh. So v is equal to the square root of gh, which equals the square root of 10 times 30, which equals the square root of 300, which equals which equals 17.3. The actual slope doesn't matter. If you had this rolling down a wall, you'd get the same answer. If you had it falling, you wouldn't get the same answer. Because there, all the potential energy goes into translational kinetic energy. So, it's not free fall. If it was a gradual slope, it would take longer to get there, but at the end, that's the speed it would have. So it's kind of curious in a way. Now, we have air resistance and all that kind of stuff. So if we tried this with a realistic situation, we'd get a slight difference between these things depending upon the angle. But I don't have to give you mass. When you think about it, we have, in this line here, you can see we have mass there, and mass there, so mass can cancel out. So that's another case where I don't have to give you the mass. If I give you it, you're not going to use it. Well, you need not use it. If you are more comfortable putting numbers in way up here, by all means put numbers in way up there. I'm just trying to model for you the idea that if you hold off on numbers a bit, two things happen. One is that you kind of see, oh, this is a very simple relationship in the end. It depends upon the gravitational field strength and it depends upon the height. It's the square root of the height, but you know. You see, you get insights by letting the letters stay in for a while. It's easy to check, like if I forgot to do the square on the bottom, so I just said v squared over r, you know, v squared over r. Once I have numbers in, I'll never spot that, but I could spot that here and say, oh, I forgot to square my r as well. So for checking, I think that leaving letters in a bit longer helps me with checking my problem, and it also gives me some insights. But when I was a student, I would probably put numbers in quite early. I didn't know it was an advantage in letting the letters run for a while, and I felt more secure putting numbers in, you know. But I don't want you to go, when it comes to test time, I want you to do what you feel most secure doing. But in between time, I'd like you to recognize, oh, by the way, if you leave the letters in longer and get used to it so you're comfortable with it, you get these two added bonuses that, you know, you can catch mistakes a bit easier, you know. But it's not required. Any questions on that? If I was to, let me just for comparison, let's just change the color for a minute. If I was to say it slid down, I'd say mgh is equal to just a half mv squared, and I would find that v squared is equal to, it would be the 2gh, it would be the square root of 2gh rather than, so it would be square root of 2 more than that. So it would be going faster if we allowed it to slide. So this is for sliding. If I used a hollow hoop, then it would be going slower at the end, and so on. It's just again, what game can I play with this? I can give you a hoop. I'm sorry, it was a hoop, wasn't it? I can give you a solid cylinder. I can give you a solid sphere. I can play with that end of things, but the rest of it is pretty much what it is. Cool. So let's